welcome to our attendees here. Welcome to what is the final talk for the semester in our Science by Diverse Scientists seminar series. To remind you, this is part of the CalVID program, and we are sponsored by the Research Corporation for Science Advancement in this seminar series. So today we are pleased to have my colleague Aurora Pribram-Jones to present. So Aurora is a professor in the chemistry and biochemistry department here at UC Merced. Her work has strong overlap with physics, which is why she's here in this seminar series, and also Aurora is affiliated with the physics graduate group here as well. So a bit about their background. So Aurora went to Foothill College at first and studied mathematics, biology, and chemistry there, then transferred to Harvey Mudd, where she did a bachelor's in chemistry, and then later went on to do a PhD in chemistry at UC Irvine, and then moving around elsewhere in California to do a postdoc at Lawrence Livermore National Lab and UC Berkeley as part of the Lawrence Postdoc Fellow and UC President's Postdoc Fellowship programs. Aurora started at UC Merced in 2018 and is currently working on various kind of problems in electronic structure related to hot, dense, excited electrons, and is part of the Consortium for High Energy Density Science that we have at UC Merced here. So Aurora is going to tell us today about her work on exploring the interplay of temperature, density, and interaction strength in the uniform electron gas, and with some comments on their path through science to get to where she is right now. So turn it over to you, and thanks for speaking with us here today, Aurora.
Thanks, David. I'm really excited to speak to this group. Let me get my talk opened up here. As David mentioned, I am in the chemistry department and affiliated with physics, but my life is pretty squarely with one foot in each as far as my research life goes. And yeah, so I'm always excited to talk to groups of physicists, and this group in particular is doing good things because I'm all about more and more pathways through academia. I guess I'll start. I mean, I know that you all know David, so you probably know where UC Merced is, but just in case, I try to give people a little bit of context. Right, we're the newest UC, and we are really nicely located in the middle of a lot of things, and we're growing really, really fast. And so I think this is up to date, but maybe a little bit behind. I think I updated the numbers recently. And so, you know, we're shooting toward about 10,000 students pretty soon. And so what I love is that when I'm at UC Merced, I feel like I'm with the people I grew up with, right? And we are very California. We look like California there, right? There are lots of folks like me who didn't have a lot of college graduates in their immediate families. About 75% of our students are first generation college students, so that's really exciting. And, you know, we have a lot of interdisciplinary departments, so I'm not the only one who's sitting with different limbs in different fields. So I enjoy that sort of environment quite a bit. And as David mentioned, I'm a member of the Center for Chemical Computation and Theory, and this is an exciting way for me to collaborate actively with other theorists in the chemistry and physics departments. And there are 5 of us that are a part of this effort funded by the Department of Energy, focused on developing theory and methods for transition metal complexes. And what's nice about being somewhere that has a lot of theorists is that for somebody like me, I get exposed to other kinds of ideas and approaches. And because I sit more in some of the fundamental theory development side of things, it means that I don't get separated as much from experimental work or from applications of the work by computational scientists, which is something that I really liked about being at the national laboratories when I was doing my postdoc and practicum in graduate school. The other group that David and I are both a part of is this Consortium for High Energy Density Science, CFEDS. David's the lead on that project. And as I mentioned before, I am very interested in figuring out how we can make more accessible educational pathways so that we get a better and more representative group of scientists doing science in all different kinds of environments, whether that's in academia or at the national labs. And so this is also funded by the Department of Energy. And a lot of the work that I'm going to talk about today is funded by this consortium because of the interest that it has for projects and goals that are important to the national laboratory system, particularly to Lawrence Livermore National Laboratory, where I did my postdoc. So this is my group right now. And so we're a mixture of undergraduate researchers, graduate students, and postdoctoral scholars, postdoctoral researchers. And what I like about having the mixture of different people at different stages is that we all can learn from one another. All of us come from different places, sort of necessarily as human beings. But I think it's really nice to have the blend of those different levels of expertise and the different experiences, because I think that we get a lot of interesting approaches to solving problems. We need that because when I go to talk to children about what I do, right, if I'm going to an elementary school or something, a lot of the time I tell them that I get to sit and imagine things and draw pictures, because a lot of what we do is thinking about physical questions and imagining, doing careful imagination, right? So thinking about how we can use mathematical physics and mathematical chemistry to describe electrons better. And so we often are using things like paper and pencil studies or trying to do numerical demonstrations so that we can play with things with exactly solvable models that we can get good answers for, or using these techniques to actually simulate complicated systems. So some of the areas that I work in with my group are ensemble density functional theory, which is a way of figuring out how we can calculate the energy it takes to go from a ground state to an excited state in a different way than is how more traditional. We also think about thermal density functional theory, which is what I'll talk about today, which is thinking about what happens to electrons when they get hot enough and dense enough that we need to think about temperature and quantum mechanics at the same time. If we take that interaction strength and think about it becoming very, 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 very strong, we can think about what happens to electronic structure when it's dominated by interaction instead of being more balanced between the energy of motion and the energy of the interaction between electrons sort of takes over. And the other project that's listed here is describing alloys. I work with undergraduate researchers and my collaborator, Professor Laurie Bassman at Harvey Mudd College, on describing compositionally complex alloys using quantum mechanics. And that's also with experimental collaborators at the University of New South Wales. And that's a really exciting program where we try to figure out how we can either suggest compositions that will lead to interesting properties or start to explain why these interesting properties are happening for these specific alloys that our experimentalist colleagues are developing by looking at things at the atomic scale. So as I said, we're mostly going to be focusing here on thermal density functional theory today. And what I'm going to do is start by talking about why we care about that at all and what it is about this work that's of interest to the national labs and the Department of Energy. So most of the time when we talk about quantum mechanics, right, we're talking about things that are at colder temperatures. We aren't ever at absolute zero, right? But we walk around when we do a lot of physics and chemistry, we walk around acting as if we are at zero temperature when we talk about quantum mechanics, thinking about only existing in the lowest energy or most relaxed state, the lowest energy state. In reality, we know that we're not at zero temperature, but for most things, most electronic systems, the next lowest energy state is not accessible at room temperature. If you start cranking things up so that you get to hotter and hotter temperatures, you may have enough energy to access that next excited state. And you start having to talk about systems that have some probability of being in this higher energy state. You also can have the chance to occupy that state if you have an excited state that's really close to your lowest energy state. So that might be something like a floppy polymer or something like that. Or when you have transitions that aren't actually just popping an electron up to a higher energy state, maybe it's something where you're just changing the spin of something, or where you have a phase transition that's not dominated by like a traditional breaking of symmetry. So changing, sometimes when we think about phase transitions, we think about melting ice, right? Going from solid to liquid, but there are phase transitions that have smaller energy barriers. And sometimes you can access those even at room temperature. When we get to much higher temperatures and a lot more of these states become accessible, we get into a situation where we might think that quantum mechanics doesn't matter anymore. But if you're looking at something like the center of Jupiter, which you have a little cartoonist picture here from some promotional materials from SLAC, the Stanford Linear Accelerator Center. Something like Jupiter is a large enough planet that the pressure on the inside is really, really high, and so is the temperature. So even though we're starting to populate these higher and higher energy states, things are still compressed enough, it's a high enough pressure that electrons still notice their neighbors, and they're still behaving quantum mechanically. And so we need to have ways of describing these electronic states that don't just take into consideration quantum mechanics, but also sort of the statistics of being in a thermal ensemble, or being occupying not only the ground state, but also these higher energy states at the same time. The other time that you might find this to be of interest is on the pathway to ignition of inertial confinement fusion. So this is the sort of thing that they do at the National Ignition facility at Lawrence Livermore National Laboratory and other flagship facilities that I'll talk about in a moment. But the basic idea that's in this diagram here is that you start with something like deuterium ice or some other fuel that's a solid, and you coat that with something called an ablator. So that might be a beryllium doped plastic, or melted diamonds, right? Like, so carbon, something really, really mellow, like melted diamonds. So you coat this capsule with this coating, and what that does is it allows you, once you put that inside, you can try to irradiate that very symmetrically with X-rays. And if you do that, you are hoping, if you do it symmetrically enough, that the shell will blast off, right? Like 3, 2, 1, blast off, like a rocket, right? It's going to blast off like this. And inside, we're going to have the fuel become compressed. So as this blasts away, the inside becomes compressed. And if it compresses enough, it will implode and release some energy. During that process, going from ice all the way through ignition into a plasma state, you pass through a phase regime that has these really high temperatures and high densities that we call warm dense matter. And so in this talk, I'm going to be focusing not on all of these so much, but mostly on these warm dense matter systems, where we're thinking about planetary cores or fusion capsules, or maybe some other astronomical phenomena. And so if we want to do that, not in the center of a planet, but if we want to do it in scientific facilities here, you really need, this is an opportunity to leverage big science, right? So a lot of these places are at universities or national laboratories where you have large teams of people working on constructing really fantastic experimental facilities, but these are high cost experiments, right? And so as you look here, we have the National Ignition Facility here in Livermore. This is the Z machine in Sandia National Laboratory in Albuquerque, New Mexico. If you see this here, this is like a catwalk, so a person could walk around here. So these are pretty large facilities. And this is the Advanced Light Source at Lawrence Berkeley Laboratory. And all of these places can leverage these massive teams and lots of resources to do very careful, very expensive experiments. But what we need in order to do that is really good theory that can not only help them plan these experiments, but also analyze the data that they get out. And so because these are difficult experiments that can't access every single set of conditions that we might want to have to learn about, say, the center of Jupiter, but also not only are they difficult, they also just are expensive. So we want to make sure that we do these things in the most in the most careful way that we can. And theory plays a large role in that, because we need to be able to simulate what we expect these experiments to do in order to design them well. If we look at, oh, it did not go. Just a moment. There it goes. Okay, so if we take a look at a phase diagram describing these kinds of phenomena that I've been talking about here, you'd have something that looks like this here. On the y-axis, we have our temperatures going from, about 100 to many Kelvin. And if we look at the x-axis, we have density increasing. Some of the things that you're used to finding in phase diagrams are sort of closer to the bottom here with solids, liquids, and gases. And as we crank up the temperature in these lower density regions, we get up to plasmas. And so a lot of the people in my field, like in quantum chemistry or in condensed matter physics, live sort of down here in the cold quantum world, the solid area of this phase diagram. And that's where a lot of my training comes from. And so what I do is I try to think about how do we adjust these methods to take into consideration the effects that are important in this sort of loosely defined region here that we call warm dense matter, using information that comes from like the long tradition of plasma science, where they have a lot of insights into these things. Plasma science and plasma science theories are really helpful for describing a lot of the properties of warm dense matter, but they don't necessarily include all of the quantum effects in a consistent way that you need to be able to describe warm dense matter. So some of my work has been about thinking, well, what if we make something that's uniquely designed for the warm dense matter regime? But a lot of what I'll talk about today is saying, okay, what if we took a quantum mechanical method and looked at what its formulation looks like when we have non-zero temperatures, and what can we do with the machinery that we already have, and where do we need to build new theoretical machinery to describe warm dense matter? Those inertial confinement fusion capsules that I mentioned are sort of, they start out solid, right? And they travel through these different phase regimes. You see that warm dense matter, where we need to have quantum mechanics and temperature effects, is sort of right in the middle here. And eventually they go past the conditions of the solar core and get up to ignition up here. So ideally, we should be able to not only figure out how to describe warm dense matter well with theory and simulations, but also talk about how this regime connects to descriptions in these other phase regimes. So it's a pretty tall order. And that's part of the reason why when I make jokes about sitting around imagining things and drawing pictures, what I'm trying to do is be really careful about how the approximations we make change in their effectiveness as we've traveled to these different types of conditions. One of the ways that we talk about these quantum mechanical systems at colder temperatures is called density functional theory. And in this talk, I'll call that DFT. And density functional theory has a pretty long, it has a wide tradition now, and it's very popular for calculating the properties of electronic systems at zero temperature. And you can see that here. If we look here, this is sort of a plot of some estimates of how often DFT is used to publish papers. And so this only goes up to 2013, so it's a little bit out of date, but you can see that the y-axis here is in kilopapers. So even in 2013, you could estimate that about 30,000 papers a year were using this method. The work that I do for thermal density functional theory, or sort of the non-zero temperature version of this theory, sometimes that can help inform zero temperature theory as well, which could potentially have a pretty big impact, right? Because we're hoping that what we do helps some of these 30,000 people use density functional theory more accurately, or with better interpretation of what they're getting right and what they might be getting wrong, or how to improve what we do at zero temperature even. If we want to talk about the zero temperature theory, we have to start with sort of saying what our assumptions are, right? What are the caveats for using this method? When I describe the zero temperature theory, I'm just going to be talking about the ground state energy, right? That lowest energy state. So when we're at zero temperature, we're not thinking about populating all those other energy states. We're just thinking about the ground state. And we're going to be talking about non-relativistic electrons, which is generally okay to do in warm dense matter because of the conditions that we're in, and sort of doesn't necessarily hold when you get up into some of those plasma regimes or certain types of zero temperature theory. But here, that's what we're going to be doing. We're also going to be talking about electrons within the Born-Oppenheimer approximation. So we're going to be assuming that the ionic centers of these materials are effectively static. So they're heavy and slow enough compared to our electrons that we can think of them as just being pinned down. They're not moving around. Their motion just affects the energy landscape that the electrons live within. And I'm also going to be using atomic units, so you won't see me tracking a lot of units here because I pretty much stay within the atomic scale the whole time. And I'm also not going to be talking about spin that often. It comes up in a couple places in the talk, and it will be obvious where that happens. But in general, all the things that I'm talking about within a spin unpolarized system where I'm not really explicitly taking spin into effect, and that all of these things can be extended to systems where spin is important without a lot of hassle. So if we want to do this, normally when we talk about electronic systems, we use an operator called the Hamiltonian, and that can be broken into a few different pieces. This is our kinetic energy operator, and this is our electron-electron interaction operator, and this is going to be our external potential operator. So this is the energy that comes from interacting with the ionic centers in the energy landscape for these electrons. If we want to look at those a little bit more carefully, the kinetic piece is talking about the motion, the energy of motion of these electrons. And the electron-electron repulsion, this VEE, is thinking about what happens between pairs of electrons and is using this pretty standard Coulombic operator that you may have seen before. And then this one body external potential, as I said, is showing us what the energy of interaction between the electrons and the nuclei in our system are within the Born-Oppenheimer approximation. So in general, describing an entire system of electrons that are interacting with one another is a terrible problem to have. It's really, really difficult to solve once you have more than a couple electrons. And in general, right, when we talk about real molecules or real materials, we're talking about Avogadro's number of electrons. So it's really a difficult problem. And so density functional theory is based on some clever ideas for changing the context of that problem and reformulating that quantum mechanical description. And so the first thing that I'll talk about, the sort of fundamental and foundational theorem of density functional theory, was put forth by Hohenberg and Kohn in 1964. And it starts by saying, okay, normally when we solve a quantum mechanical problem, we think about that external landscape that's set up by our ionic centers, our external potential. That describes our problem, and it's sort of how we name them. For those of you who have taken quantum mechanics already, right, you may be saying, okay, so I've solved some model problems in quantum mechanics. I've solved the harmonic oscillator or the particle in a box. And when you do that, you're describing the external potential that the electrons live within. Generally, we have to use that potential and solve for the wave function to describe our system properly. But that's the really complicated and difficult many-body problem that I was mentioning before is really difficult to solve because every electron depends on the behavior of the other electrons around it. And so what Hohenberg and Kohn did is they were able to show that you could actually map between not just the potential and the wave function, but a system's potential and its electronic probability density. And this simplifies your problem because instead of having to track the position of every electron in there in order to solve your problem, now you can point to a position in three-dimensional space and say, right here, I am curious about what the probability of finding an electron is. And that probability density is a simpler object mathematically. And so this showed that it was possible to talk about what the ground state energy of a system was without having to solve for the wave function. The other part of Hohenberg and Kohn's theorem is that we could rewrite the energy not only just as a functional of this density, which just means I take some function and I plug it in and I get out a number. So you can see that denoted here where I say I have some energy and by the Hohenberg-Kohn theorem, I could just write that down in terms of the density of my system, the probability density n here. And if I do that, I could say that it's going to be equal to this whole long quantum mechanical expression here where I'm doing it in terms of the wave function and I'm looking at the expectation value of each of these operators for the Hamiltonian separately. Or I could rewrite that and say, I'm going to have something that is a universal functional. So this first piece of the energy captures the kinetic and electron-electron repulsion. And then the second piece is only the external potential. What that means is that this Holmberg-Kohn functional here, sometimes called the universal functional, is true for all electronic systems. So it's always the same. The kinetic energy of a set of electrons isn't different, isn't calculated differently depending on which system they're in. We always calculate that the same way. Similarly, we always talk about electrons interacting in the same way through that Coulomb interaction. And so if we can figure out how to write this down, then we would be able to do that for all systems at once. And then this piece changes, the second piece changes with different systems that we're looking at. Unfortunately, though this told us that this was possible, it didn't tell us how to write this down in terms of the density. So this is that this exists, but we don't have a construction for how to do it. So in order to deal with that, the next sort of insight for how most modern density functional theory calculations are done today comes from Kohn again and Lusham in 1965. And there, this Kohn-Sham theorem, this Kohn-Sham idea comes from mapping this interacting system that we care about, right? The thing that we actually want to solve, to a system that's easier to solve in hope that it's easier to solve. So if we think about interacting electrons, the problem was that we had to track all of their behavior together. It was all these coupled differential equations. What if we had non-interacting electrons instead? That would be easier to solve because we could deal with each one separately and then add things up together. Unfortunately, those would have different electronic probability densities, right? Because one is interacting and one is not. But if we took those same interacting electrons and non-interacting electrons and we put them into different external potentials, we could potentially, right, make the same electronic density come out. And so I'll show you a picture of what that looks like. But the idea is that we take this interacting system and we map it to a non-interacting system with the exact same density. And if we do that, we're going to have to use a different potential that we denote here. This is our Kohn-Sham potential. So it's a different potential that causes non-interacting electrons to produce the same density as our interacting system of interest. And if we do that, we get an eigensystem to solve, a set of eigenvalue equations here. And we get out eigenstates that if we look at their individual densities and sum them up, we will get back the exact density that we care about. And their eigenvalues are here. And so these are we call these orbitals. So a lot of those things that you've seen and maybe in your chemistry textbooks are based on this idea of an orbital. And each of those have their own associated eigenvalue. Once they did that, they could take that universal piece of the energy, the Holmberg-Kohn functional, and they could write it in terms of a non-interacting kinetic energy, which we knew how to solve because we can just look at the kinetic energy of each of those electrons, those non-interacting electrons on its own, and then sum them up. We also could write out what the Hartree energy is, which is sort of the classical electrostatic repulsion, what that is here. That we know explicitly in terms of the density because it's what we do in classical mechanics where we look at the repulsion of an electronic density. And then that leaves this last piece that we name the exchange correlation energy as the final piece. Since we can solve these first two pieces exactly, and because they're much, much bigger than the exchange correlation energy, this helps us know that any approximation that we would have to make from not knowing how to write this down explicitly is going to be small. It's still very important. This exchange correlation energy is critical for thinking about things like bonding, which is, a lot, especially in chemistry, is a lot of what you're doing, right? Making and breaking bonds. And so this is a very tiny piece of the energy, but it's critical to get it as accurately as possible, even when we're approximating things. For a lot of my work, I actually think about what this object is exactly. So even though I don't have a way of doing that, of calculating that for an arbitrary system, we can know certain things about what the exchange correlation looks like exactly, either by looking at very simple systems or by thinking about what we know about these as mathematical objects. So To give you a picture of what we're doing with that cone sham mapping, you can think about the helium atom. So this is, if we look on the x-axis here, starting at R equals 0, this would be our nucleus of our helium atom. And as we go out, increasing R, we're going to be getting further and further away from the nucleus. And if we plot what the potential of that nucleus looks like, V of R, we're going to get this red curve. It's just -2 over R. And, you know, it gets very attractive as you get close to the nucleus here, and curves off this way as we get further and further away. If we looked at this is you know, the radial probability density for the helium atom looks like this blue curve. The cone sham system says, well, what if I took this yellowish brownish curve here, and I put into it 2 non-interacting electrons? If I did that, and I've drawn the correct curve here to be the exact cone sham potential, which this is in this picture, the 2 non-interacting electrons will create a radial probability density that will look exactly like that of the real interacting helium atom's electrons. If we had something more complicated than helium, we would have to use an approximation to do this. We wouldn't be able to write this yellowish curve the way that we can for the helium atom. So one popular approximation type is labeled in green here, and that potential might look like this green curve. And if we do that, what's nice about the way people have developed these approximations is that you actually get a really, really good approximation to the density. So good, in fact, that you can't see any difference between these 3 curves in terms of the radial probability density, even though there are potentials between the exact potential, the exact cone sham potential, or the approximated cone sham potential. These all look different, but their associated densities look almost exactly the same, and actually are the same between the cone sham and the exact potential. This piece of the energy that we have to approximate, and that sort of drives a lot of the, you know, the work around method development and density functional theory, is thinking about new ways to approximate this piece of the energy. A lot of the time we'll be thinking of it as a unit, the exchange correlation together, but you can separate it into different pieces, the exchange and the correlation. And some of this is based on sort of the ancestors and neighbors of density functional theory, things like Hartree-Fock theory, or many body perturbation theory, where we have expressions for the exchange that are similar to what we find in density functional theory. But you can also think of these as sort of limits of the exchange correlation in different behavior, and we'll talk a little bit about that later. If we want to define the exchange energy explicitly in 0 temperature density functional theory, we can do that by saying that it's the expectation value of the electron-electron repulsion evaluated on the cone sham system, less the classical electrostatic energy. And so it's sort of what's left over from looking at the cone sham system in terms of the electron-electron potential, what's left over beyond the classical picture. If we want to look at what this says in terms of the cone sham orbitals, we can also write down the exchange energy. Here we have spin because we can't avoid it. Exchange is a same spin property. We only can exchange electrons of the same spin, so we really have to use spin to write it down if we're going to do it explicitly with orbitals. And you can see that we do that here, and it's very similar to what you get when you look at operators in the Hartree-Fock picture. And so that's one of these links that we have between other quantum chemical and other condensed matter physics theories with density functional theory. Most of the time, I'll be thinking about them in more general terms like this or this in this talk. So that's sort of the 0 temperature picture. And so this is most density functional theory calculations that you find and that you see in the world being used today are for 0 temperature systems, or for systems that can be modeled as 0 temperature systems. On the other hand, when we start cranking up the temperature and the pressure like we have done in these systems that we're thinking about for planetary cores or in fusion science, we really need to have explicit temperature dependence built into our theory at a fundamental level. So that's what I'm going to sort of show you about here. And then we'll talk about how my group works on improving our pictures that we get from that. So when we start heating things up, instead of using just the electronic Hamiltonian that we had before with this kinetic electron-electron interaction and external potential piece, now we also have a temperature-weighted entropic piece and a chemical potential weighted number operator piece. So this is the grand canonical potential operator, because now that we have a temperature defined and you have these things at equilibrium, we're really thinking about ensembles. So here you're going to be going back to thermodynamics and statistical mechanics and combining that with your quantum mechanical pictures. And this is stuff that was done, within the first few years of density functional theory in its cone sham form, particularly by Merman in 1965, where they started thinking about how we talk about thermal properties of electronic systems. So if we do this, similar to what we had, similar to the wave function that we have when we think about zero temperature electronic structure, we still need to describe our state. And we do that with a statistical operator. So you might think of this as your density matrix if you're comfortable with that instead. But our statistical operator here is based on these n-body many-body wave functions. And we have these weights here, our statistical weights that say how much of each one of these states is, how much of that is influencing the description of our total equilibrium system here. And you can write these down as Boltzmann weights here, where beta is our inverse temperature. So it's like 1 over the temperature. And it's based on the energy of each of these different states that you could have for whatever system you're describing, whether that's your ground state, first excited state, second excited state, et cetera. Those are the ith states of that many body state that you're looking at in that moment. Our system here is an ensemble of all of those states together, and how many of them we populate heavily depends on the temperature. The higher our temperature, the more of those states will be populated. And so once we have the statistical operator described with its weights, we can talk about what the entropy looks like in our description, and that gives us our entropy operator, which is in terms of the Boltzmann constant and the statistical descriptor here. And if we want to calculate observables of our system, so, things like kinetic energies or free energies, things like that, we can do that using our statistical operator and the operator in question that we're looking at, the associated operator with that observable. And you can think of that as, since this is a trace, we can think about this as summing over different matrix elements that you have here. So you take your operator for your observable and you evaluate it based on each of these states, and you do a weighted average of those observables for each state, so as we change the temperature, we will change what the expectation value or the average value of our observables are. All this, sort of feeds into the same idea with a cone sham system, but here we have a finite temperature cone sham system. So now we're not just mapping the interacting system that we care about to a more easily solvable non-interacting system with the same density. It also needs to have the same temperature. And it means that the potential that those non-interacting electrons are sitting in now becomes temperature dependent. That also means that our orbitals become temperature dependent, and our eigenvalues, the energies of those orbitals, or the energies that are associated with each of those orbitals, also become temperature dependent. But the same idea holds, right? If we take the density of each of these orbitals and we sum them up, weighting them with temperature weights, then we will get back the exact density that we care about at that temperature. When we're doing our calculations, instead of thinking about energies a lot of the time now, we're thinking about free energies. And the reason why is because we have this entropic piece that's become a part of all of our considerations now. So if we think about our free energy, so this A is like our Helmholtz free energy, basically. And this free energy can be broken into a kinetic piece, our entropic piece, the same electron-electron interaction that we had before, and the energy of the nuclear and electronic interaction, so the external potential interaction with our electrons. We can also think about writing this down, the same energy, in terms of the cone sham system. So here, instead of having the interacting kinetic energy, now we have the individual state kinetic energies, and we can sum those up to get a non-interacting kinetic energy. We have a non-interacting entropy as well now. And now we can write out our Hartree energy, which still just depends on that density, though now that density is temperature dependent. And instead of having an exchange correlation energy, we have an exchange correlation free energy. And what that means is that it is temperature dependent and it has an entropic piece that wasn't present before. So it's a little bit more complicated in some ways and less complicated in others. They're both complicated, zero temperature and finite temperature exchange correlation. But here we do have this non-trivial aspect of dealing with the exchange correlation entropy. A lot of the time when we're thinking about the free energies here, we are thinking about the kinetic energy and the entropy together. So we often call that the kentropy. And that's when we try to actually use our Kohn-Sham system at non-zero temperatures, we have to minimize this object. So we named it so that we could talk about it as one unit. But you can see that that sort of unit comes down here in the exchange correlation as well. So we could think about this as sort of a kentropic piece and a potential piece of the exchange correlation as well. A lot of what we're going to talk about today is sort of thinking about this object here, or even just the correlation piece of that free energy. So how do we do this, right? So we've talked about how we don't actually have the exact exchange correlation energy at zero temperature, the exact exchange correlation free energy at non-zero temperature. So how can we even talk about these things together? And so what I've told you before is that I have certain tools that our group uses, and some of those are exact systems, and some of them are mathematical. I call it the mathematical toolbox, but it's sort of mathematical tricks to take a look at these things in different conditions. So one of these is thinking about coordinate scaling. So the basic idea is that if I have some density, I can either stretch it out or squeeze it. And if I do that, I wouldn't change how many electrons are in that density, right? I could have a single electronic density that I squeeze or stretch based on how I scale my coordinates. And we call it norm conserving because the number of electrons in that density doesn't change very much. So what I can do if I use this idea of scaling is I can say, okay, well, I know from writing down the equations with a scaled density that I should expect that if I have the non-interacting functional here, I can write down that the output of scaling the density looks just like the output of an unscaled density, but with a scaled scaling parameter, a squared scaling parameter. And so if I can do this for the exact system, this helps me look at whether approximations are able to do that as well. If I scale my density and put it into an approximation to this non-interacting functional, and it gives me back something that doesn't have this nice quadratic scaling factor in front of it, I know that tells me certain things about the behavior or the structure of that approximation. Another way that we can think about scaling is by thinking about temperature scaling, right? So before we were thinking about scaling or maybe I'm squeezing it or stretching it. Well, what if I took the same system and I cranked the temperature up or I cranked the temperature down? I'm going to occupy different energy levels when I do that. And I can still do it without changing. I can still do that without changing the density. And if I want to do that, instead of changing the density, I'm going to have to change the potential. And it changes a lot of different things. So we get the same kind of relationship that we had for just scaling the density if we are at finite temperature. We get that same quadratic behavior as long as we not only scale the density, but now we scale the temperature as well. So we talk about this being tied coordinate temperature scaling, and so, or tied density temperature scaling. So I can get these same nice scaling relationships as long as I change the way that I scale my temperature in a way that reflects how much I'm squeezing or stretching my density. The last tool that I'll talk about today that's pretty important for the results that I'll show you in a few moments is talking about scaling the interaction. So scaling the interaction means putting a scaling factor in front of that VEE, the electron-electron interaction. And so that means that I can change the strength with which electrons interact with one another, but I'm going to leave the density the same while I do that. And that means I'm going to be changing the external potential in order to compensate. When I do that, that means I can actually write down these same sort of quadratic scaling relationships for an interacting functional, as long as I scale not only the density, but also the temperature and the interaction strength. So this is tying the scaling of temperature, interaction strength, and density together. So this lets me really see how these different pieces in our descriptions of electronic systems are interacting with one another. How are they tied together? Are they competitive? Are they cooperative in their influence on the system? And so this is a technique called the adiabatic connection formula, and it lets us actually write down the exchange correlation energy as a function of just the potential piece of that. So we don't even need to have a way of writing down the kinetic piece here. We can do it just in terms of the potential, and we can write it down as an integral that takes me from the non-interacting cone sham system and turns the interaction strength on nice and smoothly all the way up to 1 where it's interacting with the exact system and the density stays the same the whole time. So what we're going to do is look at what this integrand is inside of this integral here. And that can help us think about different things. Here's a cartoon of what I mean by that. So this is a plot of that integrand. So what was inside that integral is on this black line here. And this is our x-axis along the top and our y-axis coming down into negative numbers here. And if we plot this black line, if we look at the area between this curve and the x-axis from 0 to 1, we will get back the exchange correlation energy. Since what we have, the value we have at 0 interaction strength for the non-interacting cone sham system is the exchange energy, we can actually draw this line across and say that we have a cartoon using this sort of geometric picture, right, for how the proportion of exchange and correlation changes over this adiabatic connection. So we can think about looking at exact curves and approximated curves and seeing how well it is mimicking this behavior as we go through different interaction strengths. So this helps us think about the proportion of different pieces of the exchange correlation and how we can best approximate them or analyze them. If we turn on the temperature, this curve shifts and we get a picture of the balance between exchange and correlation free energies. And it actually doesn't just change with temperature, it can also change its curvature quite a bit depending on the conditions of your system. And so what we do is instead of looking at cartoons of this, we wanted to look at real pictures. And that's because we really want to get a picture of this exchange correlation free energy and what happens as we shift the interaction strength. What this has let us do is we are able to look at this for an exactly solvable model system or for a useful model system that has really highly accurate numerical simulations done. And it lets us look at these objects for something called the uniform electron gas. So if we want to do that, we can use certain rules to extract different pieces of the free energy using a parameterization of the free energy of this uniform electron gas. So you can think of this as if we had electron density spread uniformly throughout all of three-dimensional space, and we can talk about certain physical properties of that system, and because it's based on some certain physical properties, we are able to trust certain types of physical behavior and limits based on those arguments. So what we can do is we can say, if I really want to pull out the exchange free energy for this uniform electron gas, I can do that by looking at certain limits of the exchange correlation free energy. And we know that if we look at high density, at the high density limit of this object with certain scaling, that I will get out just the exchange free energy. And we can combine that with ideas from that adiabatic connection approach that I mentioned before, and some of my prior work from my PhD. We can use this parameterization that we have for the exchange correlation free energy of the uniform electron gas to pull out just the correlation piece and give us the potential piece that we need to actually plot that integrand. And so that's what graduate student Brittany Harding at UC Merced in my group has done. She has used this parameterization by Groff and co-workers to generate adiabatic connection curves for this uniform electron gas. And you can see that it looks similar to our cartoon. If you sort of peel away all these other layers, you can look at this here. And as we increase the temperature at a given density, these curves shift up, and we can look at the balance here between the exchange, this area under the curve here, and the correlation, this piece that's below the dotted line and above the red line. And we can do that at different conditions. One thing that that's let us do with undergraduate researcher Zachary Mowry is think about whether these, whether the relationships that exist at zero temperature hold between the exchange and sort of the limit of how this interaction could be mathematically. And we find that it's a little bit different at finite temperature than it is at zero temperature. We don't have the same relationship between the exchange free energy and these bounds that are shown down here as we do for zero temperature exchange energy in those bounds. This has let us think about, well, what could those bounds look like? Should they be temperature dependent? And that's something that's ongoing research in our group. But we were able to sort of look at what these bounding conditions might be for these finite temperature curves. And that can help us think about how important these temperature effects are for not just finite temperature systems, but also for zero temperature systems in different conditions. We can use this sort of thing in what Zach is using for his thesis, thinking about the generalized thermal adiabatic connection, which is a way that we have of approximating those curves that Brittany's been doing for the uniform electron gas. This is a way of thinking about how do we actually approximate those curves in general. And if there are certain conditions where we might be able to use sort of a naive version of this much more involved thing. The GTAC has a bunch of different terms in it, but if we think about only certain ones mattering, they line up really nicely with things like the entropy part of the exchange correlation, which is a piece that's pretty hard to get at. And if we look at that, it's the temperature behavior of this free energy. So we might be able to connect to existing zero temperature approximations by doing that. I know we're sort of down to the end of the wire here, and I know it's the end of the day. So I want to give you a little picture of what I think is important about my path. My path has been pretty convoluted, and I've talked a lot about electron interaction, so I thought I'd talk about human interaction a little bit. This is what you get when you look at my CV, or probably lots of people's CVs, right? It talks about this educational path and what your academic appointments are. But there's a lot for all of us, right? There are a bunch of different hidden pieces of our history that don't appear there. And I think it's easy for us to forget how lucky we are to have a variety of experiences, and how we need to protect the availability of those many, many different human experiences by providing opportunity for all to get through these educational pathways. So like, these are some of the things that my path has represented, right? I went to community college because I dropped out of high school. There's been a lot of difficulty and trouble in my life that has given me very different skills than some of my peers in academia. And there's some things that connect a lot of us, but you would never see these things just from looking at my CV. And I think a lot of my colleagues have similar, all of my colleagues have similar hidden pieces of their progression. And so, I did a lot to sort of restructure after leaving high school. I've done a lot of different things. I've had many careers, but one that let me do things is by being a bookstore manager. I could study on my own and test into science programs. And that means that I come with some gaps and some additional texture, you might say, to how I think about things and how I teach and how I do research. The other thing that I realized, right, from looking at how people see my path now, my students, is that it looks like I had the idea to go to school, and because I'm really good at talking about how each of my experiences has sort of led to this culminating place of where I am now, we're hiding a lot of the other pieces of that, right? A lot of academics are taught, we are taught to present our experiences that contribute to our professional identity and maybe leave out some of the other pieces. And so I want to remind everyone that I'm not the only one that has these things, that all of us have these multiple pathways and sort of more convolution than you might see on a CV. And if you are one of these folks who is noticing this because you have that skill and that perspective to look outside of somebody's strictly academic pathway, you may realize that there are a lot of decision points, and all of us hit these. And I think that one issue that we have, and I know that CalBridge talks about this, is the idea of having a map of mentors, because the person who knows about this particular conundrum, right, like whatever this brain is, you talking to somebody else about this may not be the same person that is able to give you insight here as you're on this spot where you can really see your goal in place. Or maybe you get all the way over here and you're like, I got to a different goal than I was expecting. I think having a collection of mentoring relationships is really, really helpful. And it's something that has helped me a lot. There are lots of ways to do these. I know CalBridge has professional development activities where you work on some of these things, but I encourage you to look at different ones, because sometimes the ways that you categorize different mentors who can provide a variety of support structures for you, really just looking at different categories can help you figure out, oh, that is a thing I've been missing, and I didn't know that's what has been challenging for me. So you can see that this one is talking about maybe you need some that are emotional support. Who you have supporting you as a friend may be very different than the people you have as professional friends. And maybe you need people for accountability in different areas, and et cetera. Not everyone is good at all kinds of topics. So this really helps to prevent you from being resentful of somebody not understanding certain things that you need. It helps them not burn out. It helps you not all be, everyone in your program asking the one mentor for help, because they're known as like the mentoring person. And it helps you diversify your skills and be more resilient as a student. So I really encourage people to look for mentoring relationships, not as this strictly formal guru-based kind of thing where it's just one person that you look to for everything. I think that invites some toxicity into your life. So I hope that you, like me, are able to sort of reach out and just start exploring what those different relationships might look like. And the only way to do that is to just sort of start thinking about where you have support already and where you might need it. And if you're in a point of your life where you feel challenges, that is a good time to start thinking about what kind of support would be helpful to me right now, and where am I not getting that? How can I find a spot where that is useful? So yeah, start a draft and start to ask. That's sort of my unsolicited advice. If you find yourself on a path that maybe doesn't match up with everybody that's around you, and remember that that's true of all of us. Like we all are on a singular, like our own sort of unique path. And so you are not the only one to feel like you are on a unique path. And that is undeniably a benefit, even in the moments where it doesn't feel like it is a benefit because it is challenging. So yeah, go out and find mentors that can support you in your uniqueness and help you become your best self, and encourage you to do productive things like rest and work hard. So I want to thank the people who funded this work are it's the Consortium for High Energy Density Science. The folks who worked on this are Brittany Harding and Zachary Mowry in the group. And I, of course, also I'm very grateful not only for the land that I've done my work on, but to the generations of people that have had relationships with that land for thousands of years. So thank you very much for your attention.
Okay, thanks so much, Aurora, for speaking in this seminar today. So now we have time for some questions. So since we have just a relatively small group here, I'm just going to click allow to talk on everybody here. So you can you can just unmute yourself and speak if you'd like to ask a question. Well, or if you prefer, for whatever reason, you can also put it in the Q&A. That's also fine.
So I was curious about the name of your group, Hypogaia or whatever, Hypogaea.
Yeah, it is about this owl. So I grew up in East, I spent a lot of time in East Palo Alto on the Baylands in the Bay Area, and there were these burrowing owls, and I like them a lot because they remind me of home, but they're also endangered. And so I like the idea of making sure that we grow while protecting ourselves and our community. It's a big part of that for me. But I also think, like, we're trying to look beneath the surface a lot in electronic structure. And so I like the idea of this like wise burrower, trying to figure out how to be wise while we're burrowing. And so, yeah, but also my group has taken to the owls quite a bit. So there are a lot of owls on the website now. Good. And when people don't want to use pictures, a lot of the time they use owls.
Okay, nice. Also, I was just going to say thank you for highlighting your view about mentorship. It very much matches what we try to convey to people in Calbridge. In fact, Katie Rodriguez-Wimberly, who's listening in, would led a group of alums who rewrote our mentorship handbook to really emphasize both the fact that you need multiple mentors, and that we have a map very similar to the one that you showed. I don't know if it's exactly the same. Katie might be able to comment, but we also emphasize that mentorship is a relationship. It's not a one-way knowledge transfer. In fact, there's a lot of things that mentors can learn from mentees about their culture and different cultures, and just sort of broadening their understanding of the world and the people around them, so that they don't keep that sort of narrow view that everyone's the same in science.
Yeah, absolutely. Hi, Katie. I see you.
All right,
Hi. No, it's fine.
Yeah, no, I'm glad that you guys do that kind of work. It was something that was really transformative for me, thinking about it that way. I feel like I was searching for the perfect mentor for a long time. And I think that, especially if you're from a marginalized group or multiple marginalized groups, like, it's very hard to find somebody whose experience will be able to support all aspects of you. And I think it's almost unfair to ask people to do that. And like you're saying, we all learn so much. Like, we think about the one mentor who's really good at it in the department, sometimes getting overwhelmed. But I think that the learning that you're talking about is people doing from the mentees, right? I mean, that back and forth relationship, you lose out if you're not sort of spreading out to have more of those maps. Everybody gets to benefit from that. But I think also the responsibility of being a mentee is a lot, right? So if you're like you have this really intense, like, I think having certain deep mentoring relationships is pretty important. But I think that if you only have one, relationships have ups and downs, right? So if you only have one primary mentor, when that's in a downward spot where maybe you're not connecting the way that you always have, or you're disagreeing about something, or you're challenging one another, it can be really disheartening if you don't have sort of the buoyancy that you get from having multiple mentors. So I'm really glad that you guys talk about that in this group. I think it's really critical for sort of figuring out how to have healthy relationships in academia, because I don't think we quite know how to do that consistently yet. So I think we're all learning how to do that better and better. I think this is a big part of it. So.
Great. Any other questions out there? I think we were talking at one point regarding the idea of you doing a seminar here, or about thoughts about like training the next generation of scientists. You want to make some comments of your thoughts along those lines?
Sure. Yeah. So I think it's really important to acknowledge how unique each person's path is. And I think this takes a tremendous amount of work. I don't think that science is quite set up to reward mentors or mentees for the amount of work that development really takes. But I try really hard to listen to my trainees at whatever level they are. I don't know that I always do that perfectly, obviously. But I really try to think hard about what is best for their view of their path at the moment, because we can't know exactly where we're going to be. But that's hard. It's hard to do that. And I think having the idea of a mentoring map for trainees helps a lot, right? So there are times where I will realize, like, I'm trying to help them do something and I'm absolutely not the best person to help them with that. We talk a lot about reflection in my group, and taking breaks, and that breaks are productive because you can do better work after your break. But that a productive break sometimes means confronting difficult things as part of that. Like, you can't actually rest until you deal with the thing that's been bothering you sometimes. And sometimes you have to rest first and then deal with it and rest more. But it's hard for me to do that. I've found that I have a lot of like my own history and guilt around taking breaks and things like that. But I'm trying to build that into the way that I teach as well. We do a lot of reflection exercises in my classes, as my undergraduates and graduate students would probably complain about. And we think about things like Professor Francis Su at Harvey Mudd has talked about the sort of intellectual or scientific virtues that you try to develop in your students, even though we often are just assessing whether they learned material of a certain type in a certain way. And so how do we build in things like these reflection exercises to help people think about cultivating an appreciation of beauty, right? I mean, we want people to have that as part of their being a scientist. A lot of us have a natural inclination, we think is natural, this inclination to appreciate the beauty of the topics that we are studying and the connections between them. But we don't often talk to students, especially at early levels or sort of the in-between levels, right? Between the freshman seminar and the reflective book that you get to put out as an emeritus professor, right? There's a lot of time in between there where we're not necessarily talking about cultivating an appreciation of beauty, but we are doing it. And a lot of the time it's the thing that sustains you through the most difficult parts of your study. So I'm trying to at least introduce those topics. I mean, I do that in my freshman chemistry class, and I did it in my graduate DFT class. So like there's stuff that I do that overlaps, but I'm trying really hard to think about how to build resilience, this idea of grit. How do we help people stay tenacious, right? We want people to grab onto things with lots of gusto and be resilient to challenges, but we want to do that. I mean, thinking about things being girded with kindness, right, is a phrase that I've used before. Like, we really want the strength of vulnerability and kindness to be underlying that. And how do we do that? I don't have an answer for that. Like, I feel like I'm trying to learn to do that through my relationships with my students now. But I think that it's important to balance those things. So those are my weird musings on a Tuesday evening about developing the whole sciences, I guess.
Great, thanks. Vince, I saw a hand pop up.
Yeah. Do you think that, because since I've been in the same graduate group as both of you, I've gotten exposed to ideas like the philosophy of science, and how that was really kind of nicely tied with, quantum theory and physics before World War II. Do you think that would be something that is worth considering for students in our field, to kind of help with, I guess, trying to understand maybe the deeper implications of our research, or to understand just what is a right answer from a nonsense answer beyond just a mathematical concept of that? Is that kind of a clear question what I'm getting at?
Maybe. I will see if I understood it, right? I mean, I think you're hitting on a bunch of different things, right? I mean, there's the idea of, is this particular idea of what scientific thinking and philosophy is that valid currently? Or is it worth studying? I think it is worth studying. I don't know that we have made space in our curricula for graduate students in particular to think carefully about philosophy, or even I don't think that we require people to have training in how to think about those things coming into the sciences in graduate school. I don't think that it's bad to do that. I do a lot of ethics stuff. David and I have talked about doing ethics stuff as part of the Consortium for High Energy Density Science, right? So this is an area where you're talking about fusion science, but fusion science is also involved in things like maintaining the nuclear stockpile for what some people would call a very imperialist, capitalist country, right? So how do you balance what you're doing? Like, are you okay with your science being used for either or of those things? Do you think that funding one of those, if it might influence the funding of the other, is worth it, right? There are questions like that that are sort of natural to start talking about. And I can't, Harvey Mudd talks a lot about your impact on the world as scientists, where I did my, the later part of my undergraduate study. And I think that that's useful. I don't think that we do it in a consistent way. I think it would be good to do it. And I think it makes your work more meaningful to think about how it fits in the context of not only your own personal philosophy, but the effect on your community. So I personally think it would be good to introduce more of it into graduate study, but I don't know quite where it fits in a way that people would have the best opportunity to take it seriously and do it with like gusto, right? You don't want it to be a box that you have to check.
Yeah, exactly. Thank you.
It's a good question.
Okay, any other questions? All right, well, as it's almost 5:15, let's call it an evening. So let us thank Aurora again for a very interesting talk on a variety of topics related to her research and other things. So a virtual round of applause.
Thank you so much for having me. It was really lovely to get to talk with this group.
Thanks everybody for attending. Look out for announcements about when we get started again in the spring semester, which will be end of January or beginning of February.
Thanks everyone. Bye.
Bye-bye.